Okay, in this video lecture, we are going to be talking about Chapter 6, Analyzing Structures. So we need to define some things about structures first. We're assuming most structures are at equilibrium. And so for the equilibrium structures that are made of several connected parts, you have to think about the internal forces, as in forces between one part and another, as well as external forces, things that are applied outside of the structure, like a reaction force here or a weight applied here or a tension here. In the interaction between parts, we know that the forces of action and reaction must have the same magnitude and the same line of action, but opposite sense. So that means what, for example, member BE here acts on member CF at point E has to be the same as what member CF acts on member BE at point E. So this force and this force would have to be the same, because it'd have to be equal magnitude, but opposite sense. So one was going this way and one was going the opposite direction. And sense just means direction. Structures can be classified into three different forms. Trusses, which we're going to study in this lecture, form two force members. So that means they are straight members with only their endpoints as connections. So no midpoint forces or connections. If I have a frame, then I can have multi-forces in a member, so not just at their endpoints. So this is an example of a frame here, because this member CF has a force exerted on it on the middle, not just at its endpoints. Machines are structures, either frames or trusses, with moving parts designed to transmit and modify forces. So that's our definition. We're going to be looking more at trusses right now. So a truss consists, again, of straight members connected at joints. No member is going to continue through a joint because, again, it can only have forces at its endpoints. Most structures are made of several trusses joined together to form a special framework. So you don't just often have one technical truss structure. Each truss carries the loads which act in its plane and may be treated as a two-dimensional structure. So you can think of these as like bridge or building supports, where there's really two directions that you're carrying about forces. The third one, for like the thickness of this beams, tends to be pretty nominal. You don't care about it much. Bolted or welded connections are assumed to be pinned together. Forces acting at the member ends reduce it to a single force and no couple. So they can't support couples, and I only get two force members. Again, they can't have forces in the middle. These forces, though, can be applied in tension, pulling the member apart, or in compression. Remember when we had a cable, we said that the force had to always be pulling away or in tension. When we have an actual member or a beam or a boom or something like in our truss structure, not a cable, it can be pulling or pushing now. So be in tension or compression. So this is an example of a truss structure here from this bridge. Again, most of these members are more slender in their thickness, which is why we aren't carrying about a third dimension, but tend to be longer in X and Y, what we're going to call our two dimensions. They don't support very large lateral loads then, so this is meant to support something like a weight more, but doesn't do well if things are going across it, like winds can be a problem for them. Loads must be applied at the joints, okay? So in this structure above, I have a floor system here for this bridge that has what are called stringers going across this way, and then floor beams connecting them to transmit the loads from the floor to the point loads of the trusses that kind of make the walls on either side. There's several different styles for trusses. Typical roof trusses are shown here, bridge trusses here, like a K-truss, and there are other types of trusses you can get, but they all kind of boil down to this simple application. A rigid truss will not collapse under application of load. So what makes it rigid? It's generally a triangle consisting of three members, and it's three sides of the triangle, and the three joints represent the most basic example of a truss. If I technically had one truss, it would just be like this triangle ABC. A simple truss is then connected by successfully adding two members and one joint to that basic triangle system. So I could add member BD and CD, that's 2 members, and connect them at one joint. Or I could keep on adding triangles off and then add from A to G one member and from F to G one member and connect them in a joint, even though this doesn't form a triangle here. But if I start off with members that aren't connected more than 2 members to one joint, I do this for like this shape here, this is not a rigid truss. It can't support every load. As again, a load at point B would cause this to crumple. But this one is a rigid truss and this one would be as well. Because again, all I did off my base triangle system was add 2 members in a joint each time. 2 members in a joint, 2 members in a joint, 2 members in a joint, 2 members in a joint. How do I analyze trusses? One method for analyzing them is called the method of joints, in which you dismember the truss into all of its individual members. Number 1, this is member AC, this is member DC, etc. And I then use my conditions of equilibrium for the entire truss to solve for the support reactions. Okay, so I see then I would end up with forces at A, in this case due to this reaction force, which I could think of as X and Y components. But I'd also have the force from what happened from member AC, so you'll be pointing here onto AC, but that meant at point A it would be acting the opposite way. Similar member AD, if I assumed it was pulling this way, would have been reacting the opposite way at A. So once I take those members out and only look at this joint, I have to include how those members would react at that joint, how they would apply a force at that joint. It would always be along the direction of that member. 2 forces exerted on each member are equal, have the same line of action, and opposite sense. So like what happens with member AD here, if I assume that it's pulling away here, I could have alternatively assumed that it was pushing in either way. Then it had to have the opposite direction for what it did onto DB, for what AB acted onto DB. So if I assumed it was going to the right of how basically DB acted on AD, then how AD acted on DB is going to the left. Same magnitude, opposite sense. So I see that in a couple here, see that like in a couple here, see that in a couple here, here. Had to make sure that the direction you drew it on one member was the opposite from the other, but same magnitude. So if I had found a magnitude like for this force here, for my reaction at A, then I knew it had to be the same value here, just opposite direction. And that's how I go about solving with each joint. Forces exerted by the member on the pins or joints at its ends are directed, again, always along the direction of the member and have to be an equal and opposite to their reaction. So you get to assume whether it was pulling or pushing, but once you assume that, you got to stick with that convention. Conditions of equilibrium are used to solve for the unknown forces then at each pen. In my case is here at A, D, B, and C, or joint. And I'd have 2 N equations overall, where N is my number of joints. So I get twice the number of joints because, again, you got each reaction and its opposite reaction everywhere. Forces are found by solving for the unknown forces while moving from joint to joint sequentially. So basically, you take I'll rewrite that, at joint A, I would do my sum of my Fx forces and my sum of Fy forces. Wouldn't be super helpful to do a moment since all those forces would be acting at A. Then I'd go and I'd do adjoint ABC, sum of Fx and sum of Fy, with the idea that if I already solved from this force in reaction A, then I know this force, and therefore I know this force as well. So joints under special loading conditions. Forces in opposite members that intersect at 2 straight lines of a joint are equal. So for example, member EA here and member AC intersect at a straight line. So the force from AE has to equal the force from AC. That's really because, again, you could kind of make your coordinate system any way you want. So if I define this as like my y-axis, then I know they've got to equal each other from that. If a forces in two opposite members will be equal when a load is aligned with a third member. So like I apply this load P here, then that load is going to go along C, in which case AD is going to equal whatever AB is. The forces in two members that are connected at a joint, like if I just have two members at a joint, AD and AB, are equal if they're aligned, and they will equal a total of 0 if otherwise. Okay. So they'd be equal to each other here, or their sum of their forces would have to equal 0 at a joint here. So that's using my method of joints under special loading conditions. Another way you can analyze a truss is a method of sections. So a method of sections involves basically dividing your truss into individual sections based on where you want to look at it. When there's force in only one member, or the forces in very few members are desired, then the method of section works well. If you need to find the force in every member, though, joints probably works a little better. So to determine the force, for example, just in member BD, I can form a section by cutting my truss through this line end to end here, and therefore I have the force BD left as kind of external to this part of my truss. It could also be external to this half if I'm choosing to draw this half instead. When I leave the whole truss together, it's internal and again cancel out one direction to the other. So I kind of had to cut it. But I don't have to look at then each joint separately. I can kind of treat this whole then section as its own free body diagram. Notice that all the exposed internal forces are assumed to be in tension here, so pulling away from their joint. FBE was pulling away, FBD, and FCE. With only 3 members cut by this section, so I cut BD, then I had to cut BE and CE. I can't just stop cutting halfway through, otherwise this method won't work. I have 3 unknowns, and I can solve for it by doing my 3 equations in 2D. Sum of f of x equals 0, sum of f of y equals 0, and my sum of moments at some point equals 0. Okay, so that's looking at trusses. We can use either method of sections or method of joints. Method of sections is a little faster if you're only looking for one or a few values. Method of joints is faster if you need to find all of them.